Good morning. So today in this video we will talk about gravitation. So we already know that gravity is something we have been talking about in the past. But mostly we just focusing on Newtonian gravity. We didn't talk about Einsteinian gravity. So in this chapter I will just trying to cover both Newtonian and also Einsteinian gravitation. So as we know that gravitational force is responsible for a lot of things. For instance, it holds us to the earth and it holds earth in the orbit around the suns. It also holds the suns hold the sun together with the stars in our galaxy. It reaches out across intergalactic spaces to hold together the local group of galaxies, and also it holds together the local supercluster of galaxies. It puts the superclusters toward the great attractors, and it also slows down the expansion of the universe. As we know, the universe still in a great expansion, and also it is responsible for the black holes. And this gravity is far-reaching and very important because it's the fundamental energy, fundamental thing in our physical life. And oddly enough, it's the weakest of the fundamental force in our galaxies. And we know that gravitational attraction depends on the amount of stuffs and the materials of the objects was made of. And we know that Earth has lots of these stuffs. That's why it produces a large attraction in it. The thing is, the force is always attractive, and we know that we never repulse to the gravity. And we define gravity as a tendency for bodies to attract each other. So Newton was really the first person to really start to realize, conceptualize, and quantify gravity. And he noticed this from looking at the celestial bodies. And he realized that gravity is the reason that they move in the path. And so he quantified this relationship with the Newton law of gravitation, and that defines the strength of this attraction. For example, we have zero point 0.8 Newton or just less than 1 Newton for the attraction between Apple and the Earth, while the attraction of between two peoples is less than 1 micronewton. We know Newton's universal law of gravitation gives us this equation here, where we have two masses multiplied by itself and multiplied by this big G, which is a gravitational constant, and then we divide by distance squared between the two objects. And we can write this as a vector equation, making a position vector. So we use this idea of shell theorem, and this is the first time we are going to call it this. And it basically says that a uniform spherical shell of a matter attracts a particle that is outside the shell as if all the shell's mass were concentrated at its center. So this is how we deal with all the point masses. We just say everything acts as the center. So we can say that Earth is a bunch of nesting shells, so we can say that Earth mass is at the center. So as always, Newton's third law is going to apply here. So Apple exert force at the Earth just like the Earth exert force at the Apple. We notice two vastly different acceleration here. It is because of their individual masses. So in order to save time, I will not discuss all the checkpoints here. So you feel free to pause and check all the checkpoints here. Continuing here with the gravity, we know that we can use the principle of superposition, which is we can sum all together the individual forces using the Newton's second law, and we can find the total gravitational force on an object and due to the multiple objects around it. And if we have one object at the center here, and the other two objects in their vicinity, then we can find the gravitational force on M1 due to M2 and also M3 by adding that two forces together, just like any two vectors. Now when we are at the near of the Earth's surface, we also experience gravitational forces, and we call that acceleration due to the gravity. And that's talking about our acceleration that we experience. And we know that baby g, we can find it using the Newton's universal law of gravity and also Newton's second law, where F equal m multiplied by acceleration. And actually this equation can be used on any planet or any large bodies. We can look at the acceleration of that body by using its mass and also the distance from its center. And we know this approximately around 9.8 meter per second square. Now if you look at this table over here, we can see it varies a little bit based on where we are. Now this is the mean Earth surface where the acceleration is around 9.83. We typically use 9.8. Now if you at the top of Mount Everest, it will be a little lower because your position is higher up. And if you are at the highest crewed balloon, it will be around 9.71. At a space shuttle orbit, we look it at 8.7. And if we are at the communication satellite orbit, it will be much weaker, around 0.2 meter per second squared, because the distance from its center is very high. So we make a lot of approximation as if the Earth is uniform spherical. But if we actually calculate it and measure the baby g all throughout the Earth at different locations, we will gonna see that it varies a little bit. And there are three main reasons why it will vary. First, the Earth mass is not uniformly distributed. You can look at the graph for the approximation. And the second one, the Earth is not a perfect sphere. And the last one, the Earth always rotates. Let's talk about the rotation here for a second. Knowing that when something rotates, there is an acceleration. So if we look at an object that is sitting on a scale that's rotating, because the Earth is rotating, then it has acceleration. So it's really normal force minus its weight is going to equal that mass times minus omega squared r. And we can calculate that normal forces is not equal to its weight. There is a slight difference, and baby g is not truly the acceleration due to gravity. It is actually the acceleration due to gravity minus omega squared r. Of course, on Earth it is very negligible. Using this shell theorem, we're going to do some experiments here. Obviously, this is not practical, but theoretically, let's say we bored a giant tunnel all the way from the one end of a globe to the other side of the globe. Let's say we go all the way from North Pole to the South Pole, and we just drop an object to that hole. The object will fall all the way to the center of the Earth because of the gravitational force. But let's think what will happen as it goes toward the center of the Earth. The mass that once pulling toward the center of the Earth, well, now there's gonna be some mass over here that will be pulling it at the opposite direction. So what do you think is gonna happen to this mass as it falling towards the center? Well, we can do a little math here to show us what might gonna happen. Let's say we're gonna have constant density throughout the Earth. It is an approximation that is impractical anyway, but let's see. We know the force of attraction or the force of gravity to be equal to big G times the mass we are dropping times the mass of the Earth times by radius divided by radius cube. I'm not going to into detail of why it's going to be like this, but let's think about the distance changes when we drop this object. I'm pretty sure you're smart enough to figure this out. So if we look out all of these constants, and that reduces our force down to a negative, let's say a constant k times by our position vector, and that looks oddly familiar to Hooke's law. So this tells us that this object is going to oscillate through the earth back and forth, and it will be a never-ending pendulum. Now, big issue in this thought is the earth rotation. Let's say we could actually bore this tunnel, which is actually impossible. So if we could get the earth to stop from rotating, and we can get this tunnel, and it would be in fact actually oscillate back and forth. So with gravity comes gravitational potential energy, and we've done a bunch of conservation from this potential energy into kinetic energy. However, one little thing to tell you that it only works where one object is much less massive than the other object. And we're gonna say that gravitational potential energy of a two-particle system is written. We're going to call it U is equal to a negative big G times the two masses divided by the distance between them. You know, it looks like the force, but we have only the R, not the R squared. We know we can use it for a two-particle system. So what will happen if we have three-particle systems? So simply we can use the equation 1322 to add this individual system of particles. Now, one thing that I don't want you to get confused about how the conservation of gravitational potential energy into kinetic energy only works when one object has a larger masses than the other object. Here, the gravitational forces is always conservative. The work done by this force does not depend on the path followed by the particle, only the difference in the initial and the final position of the particles. So because of that, the change in potential energy will always be equal to the negative of the work done on the particle. And we've seen this with gravitational work, or the work we do to lift the object, that work is positive. That means the change of the gravitational potential energy will be negative. A couple neat things that come about the energy and the gravity. We can actually derive the Newton law of gravitation simply by looking at the potential energy and by taking its derivative. That gives us Newton's universal law of gravitation. And for a projectile object to escape a gravitational pull of a body, it must come to rest only at infinity, if at all. The idea of at rest at infinity, have to look, because R, it has to be infinite, where U equal to 0. If it rests at infinity, then K will be also equal to 0. So K plus U must be at least 0 at the surface of the body. So we do a little math, solve by the equation. So we get the escape velocity, which is V equals to square root of 2 times by big G multiplied by M and divided by the R. So the rockets also will have to be launched eastward to take the advantage of Earth rotational speed, and it is to reach the V more easily. Here, table 13.2 talking about the escape velocity of various different celestial bodies, where there are gonna be moons or planets or cold icy dwarfs or neutron star. So they all have different escape velocity based on this table. With gravity, we also bring in Kepler's law, which talking about the planetary motion, and really nothing new here. Kepler, same old Kepler. If you wanted to look up the histories of Kepler, actually it's kind of interesting. There are 3 of Kepler's law that is important, and we still actually use Kepler's law and Newton's law to launch rocket out there. into space and deal with our satellites that are going around the Earth. They're not completely antiquated. They are still useful. First law basically says that we have elliptical orbits and with a sun at the one focus. Second law, we have the conservation energy, angular momentum, where we sweep out equal areas in the plane of the planet's orbit in equal time intervals. That is the rate derivative a and times at which it sweeps out area a is constant. And the third law, when we get the math in Kepler, where we have the ratio of the period square equal the radius square of two different objects orbiting same center, it's gonna be equal. So from that we get a table 13.3 that gives us the periods of all solar systems. We can actually relate the centripetal acceleration to the gravitational force, and we can rewrite as energies. And we can get the kinetic energy is equal to negative u over 2. So that's the total mechanical energy of a satellite is going to be the kinetic plus the u. So when we add those together, we get a negative g times 2 masses divided by 2r. How to simplify for us that the total energy E is the negative of the kinetic energy. So for an ellipse, we substitute A for R. Remember, A is our semi-major axis, so actually we don't depend of its eccentricity, and we just use A as a radius. So the unique thing here is all the orbits pictured here in figure 13-15 have the same energies, even though they have very different eccentricity. Where some are more elliptical than others, their total energy are the same. And so it finally lands us at the Einstein and gravitation. But don't worry, we will not get into detail into this Einsteinian gravitation. Just a brief over a general theory of relativity that describes gravitation. Einstein came up with this idea of a general theory of relativity where it helps us describe gravity much more conclusively, filling the holes and cracks that Newton had and even Kepler. And it basically redefined how we look at gravity and how gravity works. And its fundamental postulates the principle of equivalence. Now, what that means when gravitation and acceleration are equivalent. If we really get down to it, it's really the same thing. Let's try this. Think of someone in a box and they just gonna drop a ball and observe the acceleration of the ball. So you are the person in the box, you drop the ball and you measure the acceleration of the ball. If you are on Earth, you will see the acceleration which estimately around 9.8 meter per second squared. Well, let's say that the same person is in a box but not on Earth, but it's outer space, and he happens to drop it and sees that it accelerates at the same acceleration around 9.8 meter per second squared. This means that the gravity that each person experiencing are the same. What's different is what's happening to this person is very different. Where the first person is stationary on the Earth, while the second person is flying through space, which gives him the perceived notion of gravity. And Einstein says it's actually the same thing. That acceleration that you experience, that is gravity. There is no difference. This is based on the fact that space and time are interwoven together, and we called it a space-time continuum. And gravity is really the curvature of that space-time continuum. I think it may sound a little screamy, but we actually find exact evidence of it. We can see that light bends around extremely massive objects. like we say black hole. We see evidence of this bending light that we call Einstein ring, where we see two stars in a different location because of black hole between us and that star. And we also even seen recently a gravity wave, and also that's proven in Einstein theory of general relativity. So we know that the stuff is true. It's a little bit crazy, but we know that it is true. One other vocabulary thing is about this gravitational lensing. We get that effect when light bends around extremely massive object, and we can see a double. There are several things that are still uncertain and unclear around gravity. Like the source of gravity itself, it's still unclear. Is it really purely an effect of curved space-time? Or is it a force between masses? Is it due to a fundamental particle, like we call it a graviton, which would carry the gravitational force? And these questions are not yet answered. There is even more theories out there that we could not answer it yet. What we find time and time again, Einstein is still correct. Not that Newton or Kepler was wrong. Newton is totally correct, Kepler also correct, Einstein also correct. He's just finally tuned and more clearly define what we think is gravity. But there's still some question out there that are left unanswered. So, as usual, please do these exercises and please collect it to the assistant. Thank you very much for your kind attention. So please, if you have any question, just send me message on Teams. Thank you very much.